Welcome to Immersed. My name is Brian, along with Praneeth and Tina will be your hosts, and Annie will be your hosts. Immersed is a new seminar series, allowing us to build community and explore how immersive technology and new modalities of manipulating and understanding data are shaping innovations across education, science, engineering, and art. These events, roughly once a month, intended to be a mix of lectures and demonstrations, tutorials, to try to offer a deep dive into both the capabilities in the immersion lab, set of capabilities across MIT, and how we can apply them together to your fields of interest. The Immerse series is sponsored by the Immersion Lab. We provide tools, people, spaces, a platform to connect the physical to the digital, bringing together researchers from across MIT, from across the communities, both on campus and off, and bridging multiple disciplines. It's my great pleasure today to introduce a student group today that's taken unique and sort of very passionate pleasure in executing on I think is a phenomenal project. So today is Immersed in Medicine. Joining us today are Trevor and Austin, Trent, Bowen, and Elazer. I'm going to share a little bit about the exciting work that they've been doing in looking at the electrocardiogram from a virtual perspective, and how to acquire it, how to visualize it, how to use sort of VR, AR tools to advance education. So please ask questions as we go. We'll post clarifying points in the chat. Feel free to chat. We'll try to hold questions to the very end. But with that, Trevor, Austin, Trent, Bowen, Elazer, thank you for joining us today. I'll turn it over to, I think, is it Trent that's sharing the screen? So Trent, take it away.
Yep, I'll take it over. So welcome everyone, thanks for coming. Why don't we start off by discussing what an ECG is, and then we'll do an exercise as you just saw. So an ECG, as you can kind of see, starts off with these stickies that are placed on, usually by a nurse or a doctor, on your chest and on your arms and leg. And so the silhouette on the right, you can kind of see a lead or these stickies on the left arm, the right arm, and the left leg. And these stickies are voltage sensing. And as you can see, they're in a specific arrangement. And the values sensed by the leads create the graphs that we know as EKGs or ECGs. And reading an ECG for diseases is what cardiologists are paid to do, but is also a science and an art, and it's a translation of something spatial that happens inside the body. So to give a sense of the physical phenomenon inside the body, let's take a simplified model and let's do an exercise. So I'm going to give you a model. I'm going to call this heart 1, and I'm going to tell you it's healthy. The next heart I'll tell you is diseased, and actually it has an arrhythmia. So as you could see, there's a lot of something at the beginning, so it's probably an atrial arrhythmia. And when we look at heart 3 looks like heart 2. So it too is probably an arrhythmia. And once we look at heart 4, and there's more than one there's more than one degree of separation away from heart 2 and heart 3, we're not entirely sure how to diagnose the heart. And so the same is with EKGs. We see a healthy EKG, this healthy graph of the electrical signals on top, and we see on the bottom left atrial flutter. And you could see there's this frequent phenomenon that occurs that is kind of present in the third graph. But is it 1 degree of separation away? Is it 2 degrees of separation away? Is the point when teaching EKGs, do we want to teach this pattern matching? Or do we want to try and get an intuition for how to translate the EKG into a spatial understanding of what is happening in the heart? If we wanted to just do pattern recognition, we are not superior when it comes to pattern recognition. So something that people are already trying to do, this study gives a huge database of labeled ECGs and echo pairs to a CNN, to a neural network. And this brain will then spit out its diagnosis. And once we input our third graph, it wasn't actually 1 degree of separation away from the healthy heart. It was a different disease. It was ventricular fibrillation or ventricular tachycardia. So let's try and understand the EKG in a different way. And I apologize for being inconsistent with ECG and EKG. So as you can see in the graph on the top right, an ECG has different pieces. The P, Q, R, S, T, and U is part of the different parts of every single heartbeat. And it turns out that the different pieces represent what's happening along the heart, the electrical conductivity, starting from the top left in this graph and moving to the bottom right. And ultimately, what the ECG is a projection of something called the depolarization vector. And doctors don't actually have to understand the depolarization vector because it's a whole lot more complicated than just understanding the patterns. They might, in the ECG, they might as well just learn the library, absorb a library, a huge database of ECGs, and that's a pretty safe bet for understanding how sick a person is or what disease someone might have. The issue though, is if somebody gets if someone gets an ECG they haven't seen before, is it 1 degree of separation away from the healthy heart? Is it 2 degrees? Is it 1 degree away from atrial fibrillation? Is it 1 degree away from ventricular fibrillation? Where do we stand? And so we're going to introduce our project. Next slide. The electro-VR-Electrocardiogram. No, I'm kidding, that would be awful. We're going to call it the VR-ECG. And so the VR-ECG is going to be an attempt at trying to teach med students, how to gain a spatial intuition for the ECG, get an understanding of what is actually happening in the heart, rather than rely on their pattern matching skills to be able to diagnose a patient for a disease. And so let's look at what to avoid before we take on the concept of the project. So as you can see, there are existing tools for placing ECG stickies on a body, and they already exist in VR. That isn't novel. But what is novel, what these tools don't actually cover, is a generation of an ECG of this graph in real time. And so even though they provide a patient to work on, it's still just a show and tell piece because it doesn't actually teach this spatial understanding of the ECG.
So Austin, I want to ask maybe a probing question, and feel free to say that you're going to answer it, and maybe it's for you or for Dr. Edelman. How easy or how difficult is it now to learn how to place leads to get a good signal? Is this something that first year med student can do after they've been shown once, or or is it how hard is it?
So placing leads, correct me if I'm wrong, any of the doctors in the room, but I believe that's conducted by a nurse. It's conducted by somebody before the doctor actually diagnoses the patient. And so what the doctor is taking home are packets of charts of these graphs in order to diagnose the actual problem. The actual exercise of putting on the leads is not the focus. However, it is an integral part in understanding the significance of each lead. It is not the actual training that the doctor needs. And so we will leave in the application that we made, we do leave the ability to put the leads anywhere the student wants in order to understand the significance of the placement of each lead. The actual placement of the lead is not necessarily going to be something that a doctor will have to do. Does that answer the question?
Absolutely. Just, I think, I'd be curious, in terms of, looking at the tool, I'm sure you're going to think about it, or get to it, but in terms of, there's the interpretation of the data you're getting and then figuring out how to get the good data, and having a tool that gives you insight into both seems to be one of the exciting directions.
Right. So an excellent probing question. We'll talk about the freedom at which a student can decide where to place the leads inside the application. And that is invaluable. That is invaluable to the teaching or training. But to just circle back, the actual idea of placing leads on a patient is something we'll leave to really train doctors when they're in a hospital. We're not relying on this tool to give doctors a feel of where to put leads on a body. But yeah, thank you for the question. Trent, do you wanna?
Yeah, I'll take it from here. So yeah, just to reiterate on what Austin said, these tools do exist today, like simple training tools, even in VR, that allow you to take a sticky, take a lead and have a human body like these pictures show and place it and be like, okay, this green colored lead goes here. This red one goes here. Okay, now I have a better spatial understanding of, a human body and where each lead should be placed on that body. But the biggest thing these tools are missing is that they don't give you they might give you feedback on, oh, that's not the right spot, but you don't actually gain any feedback in terms of the EKG graph outputs or your actual understanding of what's going on behind the scenes or in the heart based on where you place these leads. So that's one of the biggest things we tried to tackle in VR-ECG. So yeah, that leads into the question of how should we teach this understanding, this spatial understanding of where to place these leads, what's going on in the heart, and how it all interacts. So yeah, that's where our VR-ECG comes in. So in the VR-ECG, we have a VR environment where the user is actually able to perform a full EKG and show the generated graphs, the output of where they place those stickies within the environment. So the VR-ECG doesn't just teach students where to place the leads, like I've said, but it teaches them, and it gives them the freedom to experiment and place these leads wherever they want on the body. And based on how they place them, they have, EKG graphs running next to them. And they're also able to switch between disease data sets, healthy hearts, or diseased hearts and healthy hearts, and all sorts of different cardiovascular diseases, and able to see and really gain a better understanding of, if I move this lead here, or if I swap these two leads, or I can see, what is this EKG really measuring about the heart, and try to understand in a spatial manner of what's really going on based on how I perform this EKG and what's really going on behind the scenes. So why is this useful? Why do we need a VR program for this? Why don't we just, why don't we just use what already exists? So I think the biggest reasons why this is useful is, for one, to actually experiment with an EKG right now, to go beyond the tools that exist for just placing just placing leads and learning if they're in the right spot or not. To see the actual output of what you're doing and the EKG you're performing, you need a live human subject. So whether that's yourself or another person, or you're in a medical class, and basically someone's got to you got to have one person volunteer from the class and take their shirt off and lay down on the bed, and then lay down, and then you got to place all of the leads on them, and then that way you can actually see printed out on a piece of paper or on a monitor or whatever, the actual results of the EKG. So, I mean, I think it's, that kind of leads into, it's pretty obvious that, if we're able to just do this in VR, which is, giving someone a VR headset that they can take home by themselves, they're able to just, just with a cheap headset, they can really get immersed in this experience and have the entire experience of performing an EKG and seeing the results without needing without needing an actual live human heart. And not to mention, when you do an EKG in a class with, a volunteer, that person, likely has a pretty healthy heart. And so you're only ever going to get to look at healthy EKG graphs. Whereas in VR-ECG, you're actually able to choose, a variety of different cardiovascular diseases, and then see what the graphs would look like for those diseased hearts. And so I'm going to hand it off to Trevor to start talking about how we actually built this.
Yeah, so as Trent has talked about already a bit, there's going to be many parts of this program that we needed to tackle to build it, because we want to go from the ground up, having actual heart data, being able to switch between normal and disease data, and having all of the components present that a medical student might want to look at or use to actually get the full learning experience out of this program. So the first thing that we have to do here is do a little bit of data engineering, because we don't want to be just like previous programs that just take EKG data and just spit it back out at the user. When you place the leads or the stickies on the body, we want it to actually change. We want you to be able to get different results that are right or wrong, whatever the student is to do, so that they're actually learning something. It's trial and error. It's not just like reading a piece of paper or reading a textbook and just getting one result. It has to be dynamic so that the user is more engaged with the learning content. And so the way that we've done this was getting actual EKG data, real clinical data with all of the leads, and then reverse engineering that into something fundamental, the depolarization vector that Austin already talked about at the beginning, because the depolarization vector is effectively just the it's not just a plot for a graph, just something you look at. It's something fundamental to the heart that once you have it, you can do many things with it. Infinitely plus, you can put in the environment of the simulation. It's more than just looking at a plot. And then once you have that vector, we want to be able to put the leads onto a patient. You need a virtual patient to perform on. So now that we have the depolarization vector, we want to work on placing the leads on the actual patient. So we want a body that we can put our leads onto. So you can see in that image there on the right that we have our kind of virtual dummy human that we can put our leads onto. And then after that, once you place the leads, you get to generate the graphs. And so to the right of that, you can see various different plots that'll be showing our actual EKGs. And then the last part is creating a learning environment. We don't want it to just be, a person standing in the room. This image is showing us an example of just all of the pieces that are in the simulation, but you want it to be an environment that is immersive. That's one of the highlights of VR, is that you can make a student feel immersed in kind of the situation that they're in, and somewhere that fosters actual learning. So Trent, if you could go to the next slide, please. So like I said before, the first part is our data engineering, where we want to get that depolarization vector so that we can generate different plots. And so the way that we did this was we took actual EKG data from a university in Brazil that had an open source library for EKGs and reverse engineered it into this depolarization vector. And the way that that works is actually pretty simple once we look at the math. Because when you have 12 leads, that's a lot of data coming in. 12 leads that take in data, hundreds or thousands of times per second. That's a lot of data we're working at. But effectively, the depolarization vector is just a vector. It's a vector in 3D space. And so all of the leads are basically just representations of that vector. As we can see in that image at the top right with all of the different vectors on it, the 1, 2, 3, all the V's, AVR, etc. Those are all the vectors that the leads take on. So when you place the leads, you're forming that vector on the top right. But the value of each lead is just the strength of the depolarization vector in the direction of that lead. Or in other words, it's the projection of our depolarization vector onto the direction of that lead. So that means that in a 12 lead EKG, all of the leads contain information about the depolarization vector. It's a projection in that direction. So if you know the direction of the lead, then you can reverse engineer that back into the depolarization vector. So as you can see on that image on the left, we have the blue, red, and yellow circles, which are highlighting the axes on the plane, the coordinate plane. And so by using those data points, we can effectively use those as the components of the depolarization vector in each direction, so that we have a direction in the X, in the Y, and in the Z. And then as Trent played that video a little bit on the right, and if you play it again, you can see this is what the depolarization vector looks like projected onto the XZ plane. So you can see it's periodic, it kind of swirls around, and then it repeats that multiple times. That's each heartbeat is that vector moving. So yes, that is effectively how we got the depolarization vector, is by taking actual data, real data, not making it artificially or simulated, by taking real data representative of real diseases and real people, turning it into that depolarization vector. So if you could go to the next slide, Trent. So now that we have that, the next thing we want to do is getting the leads on the patient. And then when the leads on the patient are there, then we can project it and get the values to make the graph. So in that bottom right, you can see.
Trevor,
yes.
Sorry, so I just want to interrupt and ask a clarifying question. Like, so in the learning, how much of it is required sort of big data to sort of get a general, or if you had leads, measurements for one person, are you able to effectively simulate that one person? So you could have like a disease case, you only just need the results from that one disease person, or do you sort of need it over a large population?
Well, in a general sense, the EKGs for normal people will have the same shape and structure. As Austin explained earlier, if you have a lot of EKG data and feed it to some kind of machine learning algorithm, it can differentiate, normal versus disease and different diseases pretty easily. So from case to case, they're relatively similar, but there can be discrepancies within a disease itself or in the normal population. So in general, right now, yes, the approach of taking like a 12 lead ECG data for a person and then putting it into this program is effectively simulating that person's case. But in a general sense, like a normal EKG from person to person will be similar enough in shape that it's fair to make an assessment that like you can see a normal case and differentiate it from like a disease case. Like normal cases will be similar enough to each other, but that's something we can always expand upon, is adding even more cases or maybe taking the average of cases, et cetera, so that we can get more generalized cases rather than specific ones.
So just to expand on what Trevor said, I think what you were getting at, Brian, is that generally with neural nets or with AIs, you need big data in order to come to one single model. What Trevor was saying is that here we are distilling one set of 12 lead ECG data that belongs to one person into an XYZ vector, which we can generalize for a larger population. So rather than taking a lot of data and making it and saying that's one specific model, we're taking one specific person and generalizing it for an entire population. I think that's what you were kind of getting at.
So I think so. It sounds like that you have two options, right? You can take a lot of big data and create the average good person, and spatially, what's that look like? But then you could also, it sounds like it would also work that you could replicate a case for an individual, which could allow you to like then more easily program in variations in body size, body composition, specific disease cases. So you have that flexibility to be both population learned and individual case specific if that merited it.
I think that could definitely be an application. I'm not sure if exactly what I'll say right here is what you're referencing, but I think one possibility for the program that could be useful is if you take an actual EKG of someone with maybe some type of new disease, or has someone who has a readout that maybe looks less common or kind of different, then if you take an actual EKG from them in the clinic and record those values, you could reverse engineer it and put it into this program so that you could play around with it more dynamically than just looking at the paper that was once recorded. So that could definitely be maybe like a use case for this as well that someone might want to utilize.
Great, thank you. Thank you.
So as we were saying, placing the leads on the patient is the next step. And so with these leads that we've developed, they can be placed anywhere on the body and you can still get readings with them. And that was one of the big goals that Austin and Trent have mentioned previously, was the fact that you want the student or whoever's using the program to have total freedom with playing around with it and learning new things. If you make it like the simulations that have been made before, and you have a marker that tells you exactly where to put it and you can't put it anywhere else, then you're not really learning much. You're doing something that, you know, children could do in this application of just, you know, putting blocks in holes. So we want it to be larger than that. We want people to be able to put leads anywhere and you can actually see in real time the output of your decisions. And so this 3-lead system that we have right here, that we've set up so far, we only are using 3 leads. The most important 3 leads with the ability to scale up to more are using the left arm, right arm, and left leg leads, which we'll see in the next slide as well, form a structure called Einthoven's triangle, which is, you know, very important for doctors in the readouts of their ECGs. So if we could go to the next page, please. Once we put those leads down, we want to be able to generate the actual graphs. And so the leads themselves, I know the picture on the left is a little confusing, but in general, the leads don't act independently. The leads are formed between multiple stickies. So you can see in that middle picture, that triangle, the lead is actually the vector formed between 2 of the stickies, and then you're projecting that depolarization vector onto that lead. And so we can see on the right here, this is one example of plots that we've made where we have 3 different leads, lead 1, lead 2, lead 3, and our depolarization vector is actively projecting onto the leads formed between the stickies that the user has placed onto the body. And these graphs, as we'll see when we run our demo soon here, is that these graphs are moving in real time. So they're shifting from right to left, and they're moving towards the right, and they're actively updating. So if you pick up one of the stickies and move it, then all of the graphs will change. So that, like we said before, that's one of the biggest goals of the program, is the fact that as you see these plots in real time, you can move things around and see what's actually happening with the output of your data. So you can see if I move this sticky number 2, you know, a few inches in this direction, you know, what's going to change? Is that going to make my graph change to make it look like it's diseased? Is that going to make it change where it's unreadable? Is that going to keep it the same? You know, that's the point of this part of the simulation, is seeing the outcome of your actions onto the person. So if we go to the next slide, please. So right here, we'll watch a demo here of the system in real time, and you'll get to see some of those features play out.
So here we have a video of both the, well, actually me in real life playing around with the simulation, and then the view from inside the VR headset. So here we have the body, and as you can see, there's some little green markers that I actually just turned off that will help you if you know to get a general sense of where to put the leads. They don't force you to place them in any location, but as you can see, they sort of show you where maybe they could or should go. And now that I've placed the 3 stickies down on the body, we're starting to get some data read off in the graphs. So as you can see, this is being updated in real time based on the data sets we have working in the background that are calculating what those graph values should be using the engineered data from the different heart and normal or diseased heart data sets, and then also based on my placement of the leads. And here you see something that we actually haven't talked about too much that I'll actually pause on for a minute and go back to. This is a 3-dimensional visualization. And so this is something that VR gives us the ability to do that is that other programs might not. Is, you know, for us, this doesn't look that special because we're looking at it from, you know, just a normal computer screen. But if you actually go in VR, you're able to get a much better sense of the 3-dimensional aspect of this vector. And this vector here actually represents the depolarization vector, like we talked about, which is just the sort of way the electrical activity in the heart is moving. So we can actually, you know, looking at these different data sets, we can see how this electrical activity is moving in the heart and actually be able to get a better sense of that as we're performing the EKG. So this is a pretty cool feature of the simulation.
Is that something that sort of is that a trained sort of cardiologist or somebody interpreting the plot sort of already has a mental model for? Is that sort of, you know, how do they potentially use that to augment or to supplement what is current understanding?
So, or Austin, do you want to go ahead?
Sure. As of now, the two understandings of the EKG, the 2 models of the EKG, the first being electrical activity, so just a difference in voltage level measured by the stickies or the electrodes, create the EKG. And this depolarization vector as our second model. The primary one for diagnoses, the primary one for understanding EKGs is the electrical activity one. But it's still, the depolarization vector as visualized here is still taught in classrooms. It's just not the way the instrumentation works. And so it is important when understanding an EKG and understanding the different parts of the heartbeat to have that spatial understanding. But when doctors diagnose anything, all they really need is the instrumentation and that pattern recognition, which runs as just a difference in voltage measured by the electrodes. And so we're trying to reclaim and push more for Model 2 because that has its advantages. And it's seen easier in VR. I hope that.
Thank you.
Yeah, so let me back up a minute, but so here I switched to a disease data set. This is actually atrial fibrillation. So you can see the depolarization vector of the heart here that's visualized is starting to look pretty different. And it's kind of you know, moving around a bunch in this one corner. So you can see, and then of course the graphs look very different. And now we're going to switch to sinus tachycardia, look at another disease data set. So again, we can see that, you know, our placement of the leads haven't changed, but we've changed our data set and we can see a completely different readings on our graph. And so if we look back at the vector again, it's once again looking pretty different. So we hope that this program really gives you a better sense of, how a certain disease corresponds to the actual activity in the heart. And so here I just moved a lead to a completely different, incorrect location on the side of the body, and you can see how the graphs change based on that placement. It's maybe a little bit hard to tell from the video without pausing, but and now we just switch back to a normal data set. And once again, I'll just move the lead to a different spot. And as you can see, if I pause it right about here in the middle, this left side of the graph is before moving that lead, and the right side is after moving that lead. So we can see how, since I moved one lead, it would make sense that that would affect I moved one sticky, so that would affect two of the vectors. One of the vectors would stay the same. So as you can see, lead 3 stayed the same, that graph still looks the same, but we pretty much swapped lead 1 and lead 2 have sort of inverted in where they're the peaks, which way the peaks are pointing. So you can see that difference, and based on my, you can see how the program is actually creating the graphs based on my placement of the leads and how that changes. And actually, let's go back here. Yeah, that pretty much does it for the demo portion of the video. So I'm going to hand it off to Bowen to just talk about some of the modeling and creating an immersive environment for education.
Right, thank you, Trent. So as Trevor mentioned before, the strength of VR is immersion. This is the immersion lab after all. So what you saw earlier was one of our early prototypes. We have since then built the environment to be more like a hospital. So now instead of doing ECGs in an empty space in the middle of nowhere, you'll be doing a more appropriate learning environment. Next slide, please. So yeah, this location is made to resemble an actual patient's room, not actually one-to-one, of course, with some artistic creativity and liberty taken. But yeah, now you'll feel more immersed, I guess you could say.
So let's just recap everything. We'll talk next steps, and then we'll open up questions. So the way we built this application, we took healthy and/or disease data from 12 different leads. We reversed engineered and distilled that 12 lead EKG data into an XYZ vector. We allowed people to move the electrodes or the stickies anywhere they'd like on the body. And then we projected that depolarization vector onto those leads and generated the EKG charts. By having that slightly opaque marble with the depolarization vector, which changes over time, we give a spatial understanding of the overall electrical conductivity in the heart, some spatial understanding of what's happening inside the heart, and hopefully that gives students an intuition for what is going on inside the heart and match the EKG graphs with that spatial intuition. And so the next steps that this project could take, something that you can do with the project next, is finally incorporate it into the curriculum. So we'll try and incorporate it into Professor Edelman's HST class. And because this is a flexible piece of software, We'll leave the evaluation specifics up to the TAs and the professor who know the best way to evaluate the students. And they can even plug in their hardware labs. They already have a do-it-yourself EKG machine that they can bring home. And then they can plug the hardware into the software. And so that is kind of a sum up of what we've done over the past couple of months. We created a nice VR EKG machine, and we're prepared to hand it off to a class that should be ready to use it. Hopefully is ready to use it. Any questions?
First of all, I send you the virtual and physical. I'm trying to turn my video on here. The virtual and physical plots are very nicely presented and very fascinating, very multi-dimensional project. You know, as I've expressed in the past, I'm phenomenally impressed with the journey that you guys went on to get it to this point. Everything from the machine learning to the environment to really thinking about strategically how it fits into education. So thank you. We do have some questions here. There were a couple that we maybe skipped. One question, does the VR simulator have the ability to change body fat and or gender? And if so, would that also affect the readout?
So as of now, the crux of the crux of this application is the depolarization vector, which is and the leads, they generate the ECG. Changing of the physical, of the actual like person model inside the application isn't going to do much because the data is kind of pre-processed into the depolarization vector. What we could do is take somebody, we can take different people of different genders and feed in their ECG data, but changing the person inside the simulation wouldn't affect the virtual ECGs the virtual charts that you see in the data. However, varying the data is something that we'd like to represent. It's just represented by those charts. And so ultimately the evaluations will probably be something like, what do you think the profile of the patient is based off the ECG that we're generating? And so we should have heavy-set people. We should have data from heavy-set people, thin, big, small, all types of body profiles. They'll just be inputted as 12-lead data sets rather than reflected in the actual person in the body, if that makes sense.
Great, thank you. We're getting close to the time. I wanted, if Professor Edelman is still on the call, I wonder if you could opine for a moment, just in terms of like, you know, the impact in your class, potential impact in your class, and you know how this, you know, where this can be impactful both at MIT and beyond in terms of like this sort of vehicle for sort of changing how we are educating in this space.
Sure. First, like you, Professor Anthony, I'm really impressed with what the students have done, and I wonder if you can see the slide that I just put up. So
yep, it's coming through.
I want to just put this into context. What the students have done is absolutely magnificent. This is the way an electrocardiogram was obtained 100 years ago. Here's a patient. These are ceramic jars with saline or salt water in them. And as opposed to having these adherent electrodes, or what students have been calling stickies, you actually would immerse your right and left arm and leg into these. Now, the way people learned about electrocardiograms was the way in which they were represented. This is figure 4 from Einthoven's original paper. In figure 1, he started with A, B, C. By the time he got to figure 4, it was O, P, Q, R, S, and T. And so it was an arbitrary labeling of an image of a 2-dimensional representation of a complex 3-dimensional event. And so for years, people were taught simply patterns. It's a P wave or not. It's a QRS wave or not. What the students have done is important, and it is illustrated in this figure precisely. It becomes counterintuitive because it's not just 3, but really 12 different panels that we have, and are trying to ask students of electrocardiography, even physicians, to imagine what would happen if we inadvertently moved some of those complex electrodes around. And so now, with this virtual reality system, we can actually allow them to go through every permutation and combination. And the second thing, which is much more important to me as someone who teaches, especially in a place like MIT, is that I can introduce mechanistic, driving, conceptual insights to something that for the last 100 years has been taught as a pattern. And it's only by virtue of this AR, VR system, which is now responsive to education, not just VR for the sake of VR, AR for the sake of AR, but responsive to my needs as an educator, that we can simultaneously move people out of the realm of saying it's a duck because it looks like a duck into the realm of understanding why it should be that way, and then allowing them to move, as the students have beautifully said, into a place where they had never been seen before. So I want to applaud Trent, Trevor, Bowen, and Austin, because I think in a student-led initiative, it helped me understand how to teach students. And Dr. Anthony, in particular, you in the Immersion Lab, for providing them with the resources to do this kind of work.
Very good. Thank you, Dr. Edelman. And Trevor, Trent, Austin, Bowen, thank you. Phenomenal work. We are sort of getting close to the end of time here. And there was one question that came in directly. There was a question, just a clarifying one: how accurate are the signals when you place the electrodes on the wrong location? The databases are only providing the 12 lead. But if I sort of paraphrase correctly, you've learned what it would look like at any location. And so certainly there's opportunity to validate that, but you've learned what that looks like. So let me just share my screen to close and announce sort of the next upcoming talk here. Hopefully this is coming through now. So thank you to everybody for attending and participating. Our next Immersed series will be on July 28th. That'll be Immersed in Music. And so stay tuned for the type of music. It'll feature a live performance, but also characterizing what does it mean to be a musician, capturing the motion, the physiological response and the sound. So appreciating both the external and the internal of music. So with that, again, Trevor, Trent, Austin, Bowen, and Elazer, thank you for your time. Everybody, thank you for your time and attention today. And everybody, please stay safe. Feel free to reach out and ask your crazy questions for how to get into the Immersion Lab. We are here for your use. People, tools, resources, hardware to enable you to use immersive technologies in the exploration of your educational and research needs. So thank you, everybody.